Hello, chemists. This is Ms. Placino, and you're watching lesson 13.5 on electrolytic cells. In today's lesson, we're going to talk about what an electrolytic cell is and how it functions. Electrolytic cells are a very different type of electrochemical cells than voltaic cells that are covered in lesson 13.3. So it's really important to kind of make the distinction between the two. Big goals for today's lessons. First, you should be able to explain what electrolysis is and what it is used for. You're also going to be able to label the components of an electrolytic cell and write corresponding redox reactions for whatever electrolysis is taking place in that cell. And finally, understand the energy transformation that takes place in an electrolytic cell. All right, let's dive in. So the first application of our electrolytic cells is a process called electrolysis. Electrolysis basically describes a decomposition where electricity is used to separate a compound back up into its elements. If you've ever wondered how chemists get things like pure sodium metal and pure potassium metal, two metals that are extremely reactive and are never found uncombined in nature, the answer is through electrolysis. Essentially, those compounds containing our group 1 metals are mined. We're able to melt them. This is what we mean by a fused salt, which is kind of another way of saying a molten or melted ionic compound. And then we pass an electrical current through that salt. And in the liquid phase, we're able to separate it back into the original elements. So this is really, really useful and done a lot in industry. Let's take a look at this process in a little bit more detail.
The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using 2 carbon electrodes, an ammeter, and a power supply. The white powder is lead bromide. Switch on the power supply, and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now, and a current flows. In this circuit, the electrode on the right is positive, the one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps any gas, making it easier to see their colour. What could the brown gas be? The gas is bromine. Although nothing obvious appears to be happening at the left-hand electrode, pouring the molten lead bromide away reveals a small silvery metallic bead. This is pure lead. So, passing an electric current through molten lead bromide breaks it down into the elements lead and bromine. To work out why this happens, imagine you can see the charged particles, the ions, in the compound. There are positive lead ions and negative bromide ions. Once the power supply is switched on, the lead ions are attracted to the negative electrode. The bromide ions are attracted to the positive electrode. Lead ions pick up electrons. They lose their positive charge and form lead atoms. Bromide ions give up electrons. They lose their negative charge and become bromine atoms. These form a gas. Electrolysis of lead bromide only works when the compound is molten. Why doesn't it work when the compound is solid? Change the compound from lead bromide to zinc chloride and the products of electrolysis will be different. What would you expect to see happening when electricity is passed through molten zinc chloride? This time, bubbles of a very pale gas appear at the positive electrode. It turns damp blue litmus paper red and bleaches it lighter. So what gas is it likely to be? Again, nothing appears to be happening at the negative electrode on the left. But pouring off the molten zinc chloride reveals a bead of pure zinc. In industry, electrolysis is carried out on a huge scale. Massive amounts of electricity are used to extract reactive metals, like aluminium, from their ore.
Let's look at this electrolysis of a molten salt in a little bit more detail. In your notes, you've got this diagram of an electrolytic cell. Electrolytic cells have some very important differences from your kind of standard voltaic cell. For example, in our electrolytic cell, we have just like one beaker or one container where the reaction's taking place. In your voltaic cells, we split them. The oxidation and reduction half reactions are in their own separate containers. The big difference, though, is the presence of a power source. In your electrolytic cells, we use electricity, whether it's in the form of a battery or like power from a wall outlet, to force a non-spontaneous reaction to occur. So in any diagram of an electrochemical cell, if you see a power source, it has to be an electrolytic cell. In the video, we're taking lead to bromide as a liquid and forcing it to undergo electrolysis. The salt has to be molten. It needs to have been melted. It needs to be in the liquid phase, however you'd like to think of it. As a solid, it does not conduct electricity. So the salt has to be molten so the ions can move and electricity can be conducted. As a solid, those ions are in the crystal lattice structure, which is highly organized and very rigid. They are not free to move. Once the melting point is reached, those electrostatic attractions are overcome, and the ions have the ability to move freely. As this electrolytic cell is operating, lead 2 bromide is decomposed. That's all electrolysis is. It is taking a decomposition reaction or allowing a decomposition reaction to occur by using electricity. So what we see as the electrolytic cell has run is PbBr2 is going to form lead and bromine after undergoing electrolysis. You can include the phases if you'd like to. They don't need to be there. All right, so that's just kind of an overview of what's going on in this cell. Let's talk a little bit more about the electrochemistry of it all. If you look at the left electrode, we have a whole bunch of positive ions attracted to it. You can probably conclude that that electrode has a negative charge. In electrolytic cells, your electrodes are usually something that's fairly non-reactive. So you might use carbon, like graphite, like what you've got in your pencil, as electrodes. Sometimes you'll use like stainless steel, but you've got something overall that's pretty non-reactive. If we think about what's happening at this electrode, we know that we're starting with the lead 2 plus ions. And that's really what these things are. You have the Pb2 plus ions. And we know that we're producing lead, solid lead, uncombined, so oxidation state of 0. In order for this transformation to occur, lead 2 plus has to gain 2 electrons. Since our half reaction is showing electrons as reactants, we know that this is a reduction half reaction. And reduction in an electrochemical cell always occurs at the cathode. So just to continue filling out the notes a little bit, the reaction that occurs at the cathode, it is reduction. The sign of the cathode is negative. In the voltaic cell, it's positive. We see this reversal of charge, and it really has to do with the fact that we're forcing electrons to flow in the opposite direction from which they would. The half reaction is the reduction of the lead ions into solid lead, Pb0. On the anion side, the anode side of the electrochemical cell, so the process of elimination, that must be the anode. The negative ions are attracted to it, so those Br minus ions. This must be a positively charged electrode if the anions are attracted to it. And what we have going on here is Br minus becoming Br2. So let's balance that up. We need 2 bromide ions plus 2 electrons. This is representing the oxidation of bromine, and the oxidation of bromide ions into bromine. So again, we have oxidation at the anode. The anode in an electrolytic cell is positively charged. Again, we see that reversal of charge, mostly because we're forcing the electrons to move in the opposite direction from which they would. And we're seeing 2 Br minus ions oxidized to form Br2. Remember, bromine's a diatomic, plus 2 electrons. Another really common application of electrolytic cells is to electrolyze water. So this is extremely similar to what we just talked about with the electrolysis of a molten salt, except this time we're working with water. We're actually going to do this in class. So we're going to set up our apparatus as shown. We've got a little plastic cup with some water and some sodium bicarbonate, baking soda dissolved in it. We've got push pins and a 9-volt battery. And basically the push pins will already be inserted into your cup. And then you just kind of plop this on top of the 9-volt battery so that the push pins are in contact with the leads. We're going to observe the electrodes, and basically, just kind of like the sharp end of the push pin will be your electrodes. What do you think is going to happen when you start to electrolyze water, given what you've learned about the electrolysis of a molten salt? Hopefully you're thinking that we're going to start to decompose water. We're going to break it down into hydrogen and oxygen using electricity. That is exactly what will occur, and we'll start to produce 2 gases. And let's talk about what that's going to look like and what information we can get from this reaction. So instead of having you watch a video showing the production of hydrogen and oxygen gas, let's just kind of go over this diagram. So first you might be wondering, well, what is the sodium bicarbonate, the baking soda, doing in the water in the first place if we're just trying to electrolyze the water? We know that water is not a great conductor of electricity. It does self-ionize to a very, very small extent, but it's nothing substantial. So the purpose of the sodium bicarbonate is to increase the conductivity of water. We know in electrolytic cells, if we're performing electrolysis, we need to have an electrical current break apart our reactant. And since water isn't superconductive on its own, we kind of help it out. So let's think about what the chemical reaction for the electrolysis of water would be. We know that we're going to take water as our reactant, and it's a decomposition reaction, so it's the only reactant. And we're going to break it down into its elements, hydrogen and oxygen gas. Remember, both hydrogen and oxygen are diatomic, so H2 and O2. We're definitely not balanced here. Let's put a coefficient of 2 in front of water. That'll mean we also need a coefficient of 2 in front of hydrogen. And interestingly enough, you are able to tell which gas is being produced at each electrode, even though both hydrogen and oxygen are just like colorless gases. If you take a look up at the diagram, we're kind of collecting gas via water displacement. So the gas is being produced and it's forcing the water out of the test tubes. And if you look at the airspace or the gas that's being collected, you can see they're not being collected in equal amounts. If you take a look back at the balanced chemical equation, take an educated guess on which is which gas. Hopefully you're noticing that coefficient of 2 in front of the hydrogen. So every time you are decomposing water, you are creating twice as much hydrogen gas as oxygen gas. That means that this lesser collection of gas must be oxygen, and the one that has a greater amount of gas must be the hydrogen. And when you're running this reaction in class, you can actually see the gases being generated at two very different rates. One of the electrodes is going to be producing a ton of bubbles, that's hydrogen. One is going to be producing substantially less, that is oxygen. And that's happening in your water with that sodium bicarbonate baking soda present. All right. Again, we have our power source in this diagram, as we always will when it comes to electrolytic cells. And we have to have hydrogen ions at the electrode that's producing hydrogen, and of course, oxygen ions, also known as just oxide ions, at the electrode that is producing the oxygen gas. So let's dive in a little deeper to look at the chemical reactions that are occurring. So the reaction that's taking place at the cathode, well, we know that's always going to be reduction. It doesn't matter if it's a voltaic or an electrolytic cell, reduction occurs at the cathode. What does change is the sign. At the cathode, we have a negative charge. If we take a look at the oxidation numbers of hydrogen and oxygen in this reaction, we have +1 and -2 for hydrogen and oxygen on the reactant side. Then they're both like natural state elements, so 0. So the half reaction that is occurring at the cathode, it's got to be the reduction of hydrogen. We're going from H+ to form H2. Make sure we balance. And we're going to need 2 electrons to balance the charge. Move that over. At the anode, it's got to be oxidation. Again, does not matter what type of electrochemical cell you're looking at, oxidation occurs at the anode. What is different between the electrolytic and the voltaic cells is the sign of that electrode. Oxygen is going from O2- to O2. Balance up the oxygens. Now there's 2 on each side. 2 times -2 gives me -4. So that oxidation must produce 4 electrons. So if we go back to our diagram, we know that this has to be the cathode, where the hydrogen ions are attracted. The other electrode has to be the anode, and the cathode will have the negative sign, the anode will have the positive sign. I know it can be kind of confusing with those sign changes. My suggestion would be to kind of memorize it for the voltaic cell and just keep in mind that it's reversed in the electrolytic. All right, so let's wrap up and summarize this lesson. Sorry, it's a little bit on the long side, chemists. So in an electrolytic cell, we're going to use electrical energy to force non-spontaneous chemical reactions to occur. That's why we usually see a battery in those diagrams of an electrolytic cell. We need an outside source of power so that we can provide energy to get a non-spontaneous chemical reaction to occur. Oxidation still takes place at the anode, just like it did in voltaic cells, but in the case of an electrolytic cell, the anode is the positive terminal. We're forcing the electrons to kind of flow in the opposite direction as they normally would. This is why we have the sign flip. Reduction still takes place at the cathode. However, due to that sign flip, that forcing electrons in the opposite direction than they naturally flow, the cathode now has the negative sign. Again, I know I just said it, commit the voltaic cell to memory and remember that your electrolytic cell is just the reverse of that. In the next lesson, we'll talk about another application of electrolytic cells, but in the meantime, I hope this was helpful and thank you for tuning in.